When I wrote my name here in this tutorial, I honestly did not feel comfortable not putting the name of everybody who worked with me in all my bunching projects over the more than 10 years now. And as you will see that there's a lot of not only econometrics involved, but a lot of engineering on trying to explain things, on trying to see how we test things. And I learned a lot by working with all these co-authors, so I put them all there. I really appreciate all the contribution on all of them. Okay, so as you know, like we're going to explain today identification strategy related to corner bunching on the treatment variable. What do we mean by that? By corner bunching here, we mean exactly this kind of plot here. I'm going to actually use this as the running example throughout the, the presentation. This comes from a joint paper that is forthcoming at Journal of Labor Economics with Carol, Eric, who's also here, and Viviane, who's also over there. And I think Viviane is going to present later today a paper related to this paper, but more focusing on long-run effects. But the key idea that I wanted to get here is we are trying to go after the following causal effect. If the mother is working during the first 3 years of the child, what happens with the skill of the kid around age 6? But I'm talking about mother working hours. It's not necessarily, in fact, it is not a binary treatment variable. It's not whether the mother works or not, it's how many hours actually the mother works. And you will see that this is a key distinction between this kind of bunching and, for instance, the other kind of bunching, but in general, with most of the literature. You will see that it's really, in our setup here, the bunching is binary, is multi-valued. It comes out naturally. Or you just say, okay, there. Yeah, okay. So now, as you see, there are plenty of examples where the variable here, so you're holding my mouse, so yeah. Okay, thank you. So what do I mean by bunching here? You can think about here, this is the CDF, the cumulative density function of this treatment variable. And the treatment variable is how many hours per year on average over the first 3 years of the child the mother was working. So you can see 100% of the people, 100% of the mothers work 2,500 hours or less. And you can see that 2,000 hours is about full time, is about 40 hours per week for 50 weeks. So you see that about 90% of the mothers work full-time or less. You can see the part-time will be 1,000 hours, will be about 60%. But the key point here is that you will see a concentration of observations, in this case, at 0. That's what we mean by bunching at the corner. We see a concentration, we see an unusual number of people exactly at 0. And you can see here, if you look at the derivative, the slope, as you approach 0 here, there are a few, remember that the slope of a CDF is the actual PDF. So you see that there are some people working hours on like about 10 hours, 15 hours, and you can actually see this histogram of where we zoom in for the first mothers in the sample. You see there's about 10 mothers that work exactly the equivalent about 2 hours per year in the first 3 years. You see that there's some data there. Like I was saying, these kinds of concentration, usually in the corner at 0, it's a very common thing. It turns out these are actually a bunch of questions that if you find variables, there are treatment variables like that, you can essentially use the bunching approach because you oftentimes see bunching at 0. Sometimes it's at 0, like for instance, consumption of lots of things, like consumption of alcoholic beverages or consumption of cigarettes, like we talk about, but also behavioral questions like how much time I spend on TV or how much time I spend on social media. Oftentimes you see these variables are taking several values, but you see a concentration at 0. You see oftentimes a lot of people spending nothing on that. Usually for time use, it's really difficult for you to find, you not find concentration at 0. Maybe at the bathroom and sleeping, but that's it, right? And eating, I guess. But you see a lot of concentration in number characteristics. I have a paper in the past when we estimated the causal effect of crime in a particular neighborhood, and there is a concentration of neighborhoods with exactly zero crime of a given type. But also there is no reason to necessarily restrict yourself to zero specifically. Oftentimes you have minimal regulations like minimum wage, or sometimes maximum regulations like maximum amount of money that you can leave for retirement in terms of the percentage of your income. All of this could be useful overall concentration at the bunching at the extreme. So we're going to talk, Eric later today is going to talk about concentration that not only happens in the corner, but it could happen in the middle. But today we're going to focus here in this tutorial on concentration at the corner because it's by far the most common case. In particular, we're going to focus on the case at zero, okay? So now, how do you go about motivating this identification strategy? And I think it's useful for you to start thinking about that, because if you are to write a paper on all that, you want to, as you write in your introduction, you're going to go about explaining what makes this paper different from other papers. The key takeaway that I want you to get is actually the key takeaway I want you to get in this overall tutorial is that here we have multiple values in the treatment. And this is actually a key idea, right? Because if you think about it, most identification strategies that we're used to, like IVs or diff and diff, they have assumptions that once you allow for the treatment variables to not be binary, it becomes a very strong assumption. In fact, most papers actually speak about how strong those assumptions can be. And so a typical situation, of course, is just you focus on asking important binary questions. There are many things that we have contributed in general as in economics, but other fields in causal inference, understanding binary treatment variables. Like Marinho was talking in the first part of this, the tutorial, he was talking exactly about a binary treatment, a change from T0 to T1, right? There are many interesting questions that has happened. But oftentimes, if you get to observe a treatment variable that is multi-valued, oftentimes, because the assumptions are often so strong, it's a common thing among empirical people to binarize the treatment variable and then use the standard identification strategies. But very recently, there has been some efforts to explain how that actually has its own set of problems. First, the suitable assumption, the stable unit treatment value assumption will be violated if you binarize the treatment like that, or at least will be violated with a higher likelihood. And the second thing is you are making some additional strong assumptions which may have an influence in the interpretation of the results. So what we are after here is that if you are in situations like that and you want to go after a causal effect that involves a treatment variable that takes multiple values, like for instance, instead of asking what is the effect of whether you exercise, you ask what is the causal effect if you exercise a little versus a lot and things like that, right? If you are interested in these kinds of questions, it turns out that the kinds of approaches out there, they're fairly restricted. They're more like OLS-based approach, like selection observables, or sometimes diff and diff, like selection unobserved approach, where you add fixed effects. Think about 2A fixed effects. So the interesting situation like that is that that's where bunching oftentimes happens, and oftentimes happens as zero. In situations like that, you can understand the bunching approach as almost like a nested approach, where you first can do whatever selection observables or selection unobservables approach you are planning to do anyway, like you either control a bunch of observables or you actually add fixed effects. But then if you think those assumptions are too strong, one thing you could do that with bunching is that you can actually test that. You can actually test either the selection observables if you're making that assumption, or you can test the selection unobservables if you're making like a 2A fixed effect approach. And let's say that you detect endogeneity even further. You realize that those assumptions are not met. Then actually you can build on an identification strategy based on bunching, where you can now control for unobservables beyond those observables in the case of selection observables, or beyond those fixed effects in the case of a 2A fixed effects. Okay, so that's the key idea that is helpful because you can actually build on things that we already know, and we have a lot of data as well as R commands built in to do all those things. Now, another thing that is useful here, even though it can be used together with panel data, it does not need panel data. And that could be perhaps useful if we are after certain causal questions that are really hard to use panel data on. Like for instance, so Viviane is going to talk about a paper later on today where she's after exactly the causal effect of maternal labor supply hours, on the long run effects, so say, think about long run results of those kids. Instead of the skill at age 6, think about perhaps earnings of the kids. Now, it's going to be really hard if you use panel data, right? Because you either have to have a very sharp change of that, of the working hours, or because of dynamic treatment effects, it's really complicated for you to understand whether the effect comes from a long run treatment effect or maybe a short run effect that just kept happening every year because of state dependency on the treatment variable. So these are the kinds of things that are really hard to use panel data to go after long run effects. And of course, if you use an approach like bunching, you can in principle rely on variation that is purely cross-sectional to get to the identification and then observe the outcome, you observe whether that has an effect in the long run. We're going to talk about this much more clearly when Viviane discusses the paper. But the key point here is that you will see there's an OLS type of regression. So even though we do provide in my GitHub website, we do provide the code for that, you will see that it essentially relies on basic regressions and basic bootstrapping. So you will see that it can be easily done. And one thing, because it relies on OLS type of regressions, it's particularly scalable when you go after heterogeneous effects. You will see, for instance, and let me give you an example, for instance, right here. This is the same CDF plot I showed before, but for 4 different groups of the population, depends on the skill of the mother. So you can see that you do find bunching essentially everywhere for those 4 types, although of course some bunching is more pronounced for some groups versus another. That is useful, for instance, because as you are very aware, for instance, if you use an IV, oftentimes if there is a lot of endogeneity, by the sheer fact that there's a lot of endogeneity, chances are your complier group is going to be a fairly non-representative set of the population. So it's really hard for you to go after heterogeneous effect by the sheer fact that you get to solve the endogeneity problem. A classic problem, for instance, in this literature is that they use EITC shocks as an IV for working hours. They treat working hours, most of the papers treat working hours as a binary variable. But they have a very helpful, very good validity assumption there. But then the problem here is that EITC shocks are predominantly coming from low skill mothers. So it's going to be hard for you now, conditional compliers, to focus about whether this effect is going to be different for low skill mothers versus for high skill mothers. So you, by the sheer fact that you're solving your endogeneity problem, because the source of variation you're exploring is not sufficiently abundant, it's going to be difficult for you to go after heterogeneous effects. And you see here that this approach is relies on variation that is going to be more abundant, and that would allow you to go after heterogeneous effects along several dimensions that you otherwise would not be able to. So now let's actually explain the key idea. This key idea comes from Carroll's original paper. We all know that causality and correlation are not the same thing, right? But now we're just going to use the classic decomposition that we use. Think about like Angry's textbook, right? You think about what we observe, that's what we call the correlation, right? Which is the average outcome among the kinds of people, the kinds of mother that work, say, 1,000 hours or 500 hours and so on, versus the average outcome among the kinds of mothers that do not work, they work 0 hours, right? That's exactly what we observe. And if you use the notation of potential outcome, this is exactly the potential outcome if that mother were to spend the hours, that is like say 1,000 hours, and this is the potential outcome if that same I mother were to spend 0 hours. That's just notational potential outcome. The key decomposition that you see in any textbook these days is this decomposition here, where essentially you can write this between the three. So I'm just adding and subtracting these 2 terms here. They're like adding 0, right? Those 2 terms are identical. So you essentially have an ATT, an average treatment effect on the treated, that is the potential outcome of that mother I if she were to work the hours versus if she were to work 0 hours among the group of mothers who actually work the hours. This is an ATT, right? Average treatment effect on the treated. And this is the selection effect. You can see here that this is the untreated potential outcome, the potential outcome if that type were to spend 0 hours on working, but among different types of people. This is the type of person that spend the hours versus the type of person that spends 0 hours. Of course, the key idea here about most identification strategies to figure out a way to eliminate this part, right? We need to figure out a way to eliminate the selection effect for you to get the treatment effect, right? And if you think about IVs, experiments, RDDs, different diffs, all of that has to do, or selection observers for that matter, all that has to do with figuring out ways of making assumptions that eliminate the second term, the selection effect, so you go after the treatment effect. What we're gonna do in these approaches are gonna be the opposite. We're gonna go directly after isolating the selection effect. We're gonna figure out ways of turning this off, the selection effect, and therefore identifying the selection effect. Of course, you can always get the treatment effect by taking the difference afterwards, because we always observe this part minus this part that we get to identify gets us the treatment effect. So that is essentially the key main idea, and I'm going to explain to you why bunching can be leveraged to isolate the treatment, the selection effect, and turn off the treatment effect. The key idea here, this is exactly the CDF I just showed you. I showed you this is the empirical CDF of the treatment variable that goes from 0 all the way to 2,500 hours per year for the first 3 years. And this is a theoretical picture that I wanted you to see about the potential outcome, the untreated potential outcome. Think about that as a type of the mother or a type of that child. Remember, the outcome is on the child's cognitive skill. So you can think about, for instance, among the mothers that work 2,500 hours, let's see over here, maybe the average type of the mother or the average type of the kid, an overall average type, is going to be somewhat similar, but a little bit different from the average type of the mother that works like 5 hours less. And you can keep going, like there are going to be some differences there. They could be sort of like smooth differences, but there will be some smooth differences there. But something really different is going to happen exactly 0. At 0, there are several types of people there that are getting concentrated exactly there. Why? Because not only those mothers that have a type that is just a little bit at 0, like for instance, if I give the mother a little bit of a nudge, she will already start working, right? Those mothers will be exactly just to the left here. But some of the mothers maybe are disabled, and even if I give her that kind of small nudge, they will not be willing to work still, right? So in other words, there are several types of people here that get concentrated at 0. In other words, this dot here, which is the average of all this dashed line, is essentially suggesting that there may be a discontinuity in the untreated potential outcome exactly there at 0. And that matters, right? Because that could explain exactly what we actually see in the data. What we actually see in the data, and this is the actual outcome, the cognitive skill of the kid at age 6, you actually do see a discontinuity in the outcome, exactly at 0. Now, as you all know, when you see a discontinuity in this term, that can only be explained by a discontinuity in the treatment effect or a discontinuity in the selection effect. So now, here's what I want to assume, and this is going to be essentially a key assumption that is going to be throughout this whole tutorial, right? The key assumption is continuous treatment effect. What do I mean by that? Imagine if D here is like a minute. I'm looking at mothers who are currently working a minute per year. If that mother, think about causal, so it's potential outcome. If that mother were to go and stop working, suddenly the brain of the kid is not going to explode, right? It's not going to rot in the brain. The kid is not going to go. This discontinuity we're finding here cannot be explained by the causal part. It cannot be explained as the mother working 1 minute per year versus 0 minutes per year. And the reason that discontinuity happens, that discrete change happened, was exactly because that mother actually worked that 1 minute. Does that make sense? That's the key assumption that we're going to assume this away. We're going to say that as D approaches 0 from the right, this whole thing is going to go to 0. That is the isolation. That is the way that we get rid of the treatment effect that we talked before. Now, this leads all that discontinuity that we observe in the outcome here to be explained by this discontinuity But here, so far, I'm just showing us in theory what is happening, right? Thus far, that's just a theoretical plot. So it turns out that there's lots of evidence you can show to argue why the type should be discontinuous. For instance, if the unobserved type, like the untreated potential outcome, is varying discontinuously, then it better be key variables that are covariates that I just happen to observe in the data better vary discontinuous too. And that's what we see. For instance, this is the exact AFQT score, the skew of the mother. And you can see that discontinuity is exactly at 0 as well. Again, I'm not suggesting that that is a full proxy for yi of 0. What I'm saying is that if yi of 0 is very discontinuous and I cannot check that directly, at least you see that the observable variables are very discontinuous. You can see another observable variable here, whether the spouse is present at the birth of the child, is also discontinuous. Again, the key idea here is that the moment I assume continuity of the treatment effect, then it must be the case that whatever discontinuity I observe in this plot here must be coming from here. By the way, how to implement this? This is exactly like we're doing in RDD. I do a local polynomial here for all the positive values. I choose a particular bandwidth. In this case, the bandwidth is 400 hours per year. And I do the mean of 0 separately. That's exactly what I did here. And I represent the confidence intervals of that. Similar to in Stata, you use L poly. Okay? So now, so in principle, you wouldn't need to show the discontinuity in observables, because the moment you are okay with the assumption of continuity of treatment effect, the moment you show the discontinuity in the outcome, it must come from discontinuity in the selection effect. But of course, you can provide a little bit more hand-holding for your reader by showing that observables do vary discontinuous. Does that make sense? Okay, so now let's actually talk exactly about what is going on here, because it turns out that this itself can allow us to isolate the selection effect. So just to be clear, this is exactly the plot of the average outcome for every value of the treatment variable. And exactly that's the potential outcome plot that I presented in a theoretical way. But like I just showed you, right? Those observables are varying discontinuously there. So it's possible that selection on observables can handle the problem. After all, it's possible that the full discontinuity that I observe here can be traced by the discontinuity in those observables, which in turn may affect the outcome. So how can you handle that? You can actually hold those controls constant. How do you do that? Here's the way we can implement. We can implement this in 2 steps. First, you can restrict yourself to observations at 0, and you can run a simple regression of the outcome on a constant and all the controls. X here means controls. Just to be clear, you don't need to add controls linearly here. You can do fully non-parametric. This is not an issue, okay? But the point here is that however way you decide to estimate the controls, you're going to get a gamma hat there. And then in the second step, you're going to just now plot instead of the outcome like I was plotting before, you get this residualized outcome where it's just the outcome minus the effect of controls on the outcomes. But here, notice that I'm doing, and this goes back to what we do for instance Stata. When you do the regression here, you do a regression of a subset of the sample, but when you do an outside sample prediction, you don't necessarily restrict yourself to inside the sample. That's exactly what I'm doing here. I'm doing an out of sample prediction because even though I restricted myself to d equals 0 here, I'm doing this for all observations for each value of d here. Does that make sense? So that's what I'm actually doing there. And of course, that plot is helpful because that plot is telling us, because all these X controls are all predetermined, they are not caused by the treatment variable, I know the ATT did not change there. So this is the ATT plus the selection effect. But now that's the selection effect of the part of the potential outcome that is orthogonal to controls. So the key point here, as you can see in this plot, I want you to pay attention to this plot, please, for now. The moment I add controls, look what this plot looks like. Again, it's a theoretical plot, but it looks like this. You see that the slope change a lot? just to be clear, if there was no selection on observables, if selection of observables was enough, if just controlling for controls will be enough, this will be flat, right? That means the potential outcome does not change depending on the type of person, depending on whether the person chose 1,000 hours or 2,000 hours. It will be flat. But of course, it still varies, suggesting that there is still some endogeneity. But the key point here is that not only when you go from no controls to controls, not only the slope changes, the discontinuity over here changes as well. And that already gives the key idea in Carroll's original paper, the idea that there is going to be some form of relationship between what is happening on the positive side and what is happening with discontinuity. For instance, you can think about the idea in the extreme case of no endogeneity. Let's say that I do have a selection observables approach, so that the moment I control for X, I'm done with my endogeneity problem. Then it would look more like this. It will look like horizontal there, but what will be the average of this dashed line? The average of this dashed line would be exactly the dot, the black dot. There wouldn't be no discontinuity. But if there would be no discontinuity, how then would I be able to explain the actual discontinuity I do observe in the data, right? So the key idea here is that we do know that after I residualize the plot, and you can see this is the plot with outcomes, without controls. Look what happens when I residualize that outcome by taking out its effect on controls. This is what happens. Not only, again, the slope went down, but also the discontinuity went down a little bit too. This is exactly the same y-axis, just for you to be able to compare. So essentially, the key idea here is that the reason why there is still discontinuity here is because there is still endogeneity problem after we add controls. That is the key idea, because if there was no endogeneity like this, I wouldn't find a discontinuity in observables. And because I'm assuming continuity of the treatment effect, that would mean the outcome would not have been discontinuous. So that is the key idea. Now, just to be clear in terms of implementation, this is my recommended approach, which is, this recommendation approach came straight from Carroll's econometrical paper, which is just to restrict yourself in the first step to the treatment variable equals 0. But oftentimes, if there's not much bunching as 0, you might have a hard problem actually running this regression. So actually, it's totally fine to run this regression instead. You now restrict yourself for the positive side, but the problem here is that now you need to specify what is the average causal function here, in principle, right? You need to specify how D enters there. Of course, when it was 0, there's no D there by definition because D is always 0. So you actually can make it, it's actually more kosher to do that. But at the end of the day, I have to say, in all my applications thus far, it has never happened that I got a gamma hat that was sufficiently different for each other when I do one approach versus the other approach. And the second step is identical. Okay, now, what I wanted to get here thus far is this. I hope by now you're starting to see like a common theme, and you will see in all papers that are using this kind of methodology, there's going to be this recurring theme throughout all presentations, which is this idea that we're sort of doing a little bit of a, let's say, extrapolation. What we are saying is that whatever is happening in the positive side somehow shows up somewhat in the negative side in ways that I cannot observe. I do observe the outcome discontinuity, but I have no, and I will be able to say that the fact that this outcome discontinuity is a positive discontinuity, you go from 0 and you jump up in the outcome, I do know the discontinuity must be an up discontinuity in the yi of 0. I do know that. But that part, this solid line, I honestly have no idea, right? Because I do not get to isolate the treatment effect versus the selection effect. I cannot isolate just the selection effect in the positive side. I just get to isolate that at 0, and that's why I know the sign there. This is going to matter a lot, but just to be clear, right now, just for detecting endogeneity, you don't need that at all. Just for detecting endogeneity, the fact is, so you might be thinking, wait, Greg, thus far, you show me that there is endogeneity at 0. But can you really tell me that there is endogeneity in the positive side? Honestly, thus far, I cannot, right? Because it's possible that this plot does not look like that. It just maybe was like that, and it just went like that, like the dashed line afterwards. I can show you more evidence of this later. Now, still, for just detecting endogeneity, this is all you need, because the fact is d equals 0 is part of the subset of the sample of the data. So if you already saw enough evidence of endogeneity in part of your data, you do have an endogeneity problem. So if your goal was to detect endogeneity, you're done here, right? And just to be clear, remember the X does not need to be observed controls. It could be, say, generated regressors, or it could be fixed effects, okay? I'm just using some bad notation here to think about X as potential fixed effect, but you can think about fixed effects there as well, okay? And that matters, right? Because if you have, say, the classic 2A fixed effect as part of the X here, or even if you have observed variables plus 2A fixed effect, then you are doing some form of conditional version of the what Brent and his co-authors call the strong parallel trends assumption, which is mostly related to the idea of what we typically call parallel trend assumption together with some kind of correlated random effect. When all those things, you are making that assumption and you still find a discontinuity at 0, that means that assumption is not valid. Now, what we're gonna go next is, what can you do next? So this is why I meant that it's a nested approach, because you can do exactly the baseline approach that everybody's used to, and it will trigger you to use actual bunching only after you find evidence that the previous baseline approaches do not solve the problem that you want to solve. Does that make sense? So now let's go for talking. Thus far, I spoke only about how to detect endogeneity. Now I'm going to try to talk about how you get to solve the endogeneity problem if you found actual evidence of endogeneity. And again, by endogeneity here, I mean after you control for either observed covariates or fixed effects or whatever you do there, depending on your baseline identification strategy. Of course, the baseline identification strategy could be just simple means and you don't do any control. That's a possibility, sure. Now, going back here, I'm going to start with the weakest possible assumption in this framework that we came up thus far, okay? And then I'm going to actually show you that there is an actual menu of assumptions very similar to what Marine was telling us before. The first idea here is that I wanted to argue with you that the moment you already see this discontinuity here, there is something useful here, because as you know, because of the decomposition, the correlation, which is what we actually observe, that's the slope over here, it's pretty much around 0, right? It's like, that's an approximation, but it's kind of flat, so it's kind of around 0. That is essentially the treatment effect slope plus the selection effect slope. And again, by selection effect, I mean the part of the selection after you take care of controls, okay? Selection unobservables orthogonal to control, to observables. So now, the moment you know that this slope, which you don't know, and this slope, which thus far you don't know, equals to this slope, which you actually know, this slope is about around 0, right? Because you observe straight in the outcome. There are a few assumptions that you can make to actually make progress in this. The first set of assumptions I'm going to suggest here, this is the classic thing that I think you often get qualitative results already with those assumptions, is the following. The first is the part of the assumption that makes sure that you're going to attribute 100% of that discontinuity towards what is happening here and not towards the treatment variable. There's continuous treatment effect, meaning all the discontinuity you see in the outcome is due to selection, okay? That's the first one, which we discussed already before. If you are interested in the FAK, in the frequently asked question, I could talk to you, what happens if there is discontinuity? It turns out there is something you can do still about that, but that will depend on some kind of rank condition. We can talk about this later. Now, the second part here is we're gonna make an assumption. This is the big assumption here. We're gonna make the assumption that whatever is the selection direction I find that to be, which I know to be positive, it's a positive jump here. The reason I know it's a positive jump at 0 is because there was a positive jump in the outcome here. I do know it's a positive selection there, right? Of course, you can go further. You can provide much more evidence before, like showing those observers I told you about. You know that skill tends to be a positive characteristics that tend to affect the cognitive skill of the kid. This is the skill of the mother. And you do find this continuity of this key variable, and that suggests there is indeed a positive kind of selection, right? Similar to like usually, contrary to what Carol might say, having a husband around can help with the cognitive skill of the kid. And and actually, you see that some discontinuities here, suggesting that yes, there is some low type as 0 compared to just a minute there, right? So you do see some evidence based on observables that there is a discontinuity on the type. But the key point here is you can go this directly just by showing that the outcome is discontinuous. And its continuity is a positive continuity. You go from 0 to a 1 minute, it jumps up the outcome. So you know the potential outcome after you take care of controls must have a jump that is positive. But just to be clear, that does not tell us what happens in the positive side here. That only tells us what happens there. So now I need to make the assumption that I'm going to extrapolate that the direction, I'm not saying the same quantity, but the direction, which is positive, happens to also means that it's going to be positive here. That's exactly allow us to say that this part here is positive. But because this part here is positive and this part here turn out to be close to 0, we already know that the causal effect must be negative. The only way that that thing should be around 0 is in this, if indeed, as the mother is working longer hours, the kid is actually, their cognitive skill at age 6 is getting harmed. Does that make sense thus far? That's what we know. We understand those things based on two assumptions: the continuity of the treatment effect and the assumption, which thus far I did not show how we can test that, but I'm going to show you later how we can actually test that. The assumption that direction as 0, the direction of the selection as 0, which we get to observe, is the same as the direction of selection in the positive side, which we don't get to directly observe. Okay? So just to give you a sense, imagine if the opposite happened. Imagine if this happened instead. So this assumption would be wrong. If this will happen instead, then in reality, the selection effect would have been negative for the positive side. And in reality, I should have, the true value would have been positive. But unbeknownst to me, I would be making this assumption, and I would say that is negative. Okay? That is the key way that, as we will see here, this is a key violation of the assumptions that we're talking about. When this happens, this is going to become a problem here. Just to be clear, David Slichter is going to present a paper later today where he's not going to assume that. He's going to allow for the possibility that this thing could, even this plot like that could happen. Of course, we're going to make a different assumption in that situation. But everything that I'm going to show in this tutorial today here, I'm going to make this assumption here. And I'm going to show you how we can actually use controls to test that. Okay? But that is the first idea, that this set of assumptions, like I told you, will give us something good here, which is a very good already qualitative result in that setup. Of course, sometimes it just happens to not be the case. So for instance, if the plot that you did turn out to have a slope that will be positive here, then just by knowing that delta, that the selection effect is positive, cannot tell you anything yet about the treatment effect, whether it's negative or not. It just happened, and in this case, it did tell us, okay? So what I'm saying here is that sometimes the bounds will be perhaps less meaningful than it just happened to be here, but we have several papers where the bounds turn out to be extremely meaningful already, that we could say whether the effect will be positive and negative. Okay, so now I'm going to go further here because I'm going to essentially start imposing additional assumptions in order to actually make more progress to find not only these bounds, but actually I'll try to go after point identification. I'm going to try to actually estimate the effect. The key idea here now is I need you to pay attention here, because I think I would say that this will be the most non-standard part of this method now, is something that is kind of obvious when you start thinking about it, But because we're trying to be more, because in the standard approaches, we just need to figure out a way of getting rid of the selection effect. But now, because we need to go and identify the selection effect, we need to be a little bit more careful in understanding what that selection effect happens to be. So for you to understand this, I think it's useful for us to create a new notation here. So let me explain to you what do I mean by the new notation. You can see here that the treatment variable, which is, sorry, the treatment variable, which is this variable D here, is kind of playing two very different roles. And we somehow, in standard econometrics, we call that treatment variable. It's playing the role that how it enters inside the potential outcome, like how would be the counterfactual of number of hours the model actually works, if either D or 0 in this case. That's actually the true number of hours that the model actually works. But now, as a conditioning here in red, you can see that this role is a completely different role. The treatment variable now is playing the role of a selection variable. The kinds of group of people, the kinds of people you're conditioning among certain kinds of people, the models that actually work the hours, or the models that actually work 0 hours. So we're going to use here a different notation here. Whenever it plays the role of the selection variable, we're going to call that a selection variable, and we're going to call that, put a star there. Okay? Whenever it continues being a treatment variable, it's going to be a regular treatment variable. That's going to be useful here as just a notation. Thus far, I made no assumption, but you will see that that's going to be very useful for you to think about that. And you can see here that I did not put a star at 0. The idea that I did not put a star here is exactly because, as you know, at 0, there's going to be a concentration of that variable, that selection variable. There are going to be many D stars when D equals 0. There's going to be many different selection values, the values of the selection variable, when the value of the treatment variable, which is actually 0, is kept constant. And that's what allows us to isolate the effect of the selection variable. Now, let me actually be more precise and try to explain what do I mean by that. Actually, you all know we already discussed how the untreated potential outcome could look like in theory. But now I'm going to just say what is the average type of the model. By type, I mean the selection value of the selection variable, the average type among the models that choose exactly, let's say, 2,000 hours or 1,500 hours and 1,000 hours and so on. And you can see here that they are, by definition, there's going to be exactly the 45-degree line here. Thus far as I just calling the selection variable as the type of what led the person to choose this positive value. If you are the kind of model that choose 2,000 hours, you will be the type of model that choose exactly this type of hours, okay? Just to be clear, I want to be clear with you all about this. Among the models that choose 2,000 hours, there could be several different types there. It could be some models that chose 2,000 hours because they are workaholic, even though they have a lot of problems with childcare, they manage to figure out a way how to work 2,000 hours. There are going to be some mothers that have no childcare problems, but they are not workaholic. They still lead them to choose 2,000 hours. For now, I'm just going to call that person, they all both have the type DI star equals to 2,000. But we're going to show that the idea that there may be many factors that lead to that potential outcome, the untreated potential outcome to be there, is not going to necessarily affect our problem, and I'm going to discuss later, okay? So in other words, I'm not saying that D star is a single index situation. So for instance, what Marinho was discussing before, he was talking about a single index situation in that situation, that you are equal up to a parameter, right? We're not necessarily saying that there could be heterogeneity in principle, there could be heterogeneity exactly like we're seeing here, an observed heterogeneity that is unrestricted. But here's what I'm going to do, and that is going to be the key assumption. But first, I'm going to make this assumption that the potential outcome, the untreated potential outcome, is going to be written as a linear equation of that D star. Okay? This is yet not an assumption because I did not tell you any property yet of eta. I'm going to tell you in a few minutes that. But the key point here is that the point that we discussed before, right? The average type among the models who choose exactly 0 should be somewhat negative because you're doing an average of all these dashed lines. That's exactly what we discussed before. I'm just using the same notion of the, discontinuity now, but instead of the y0 that we discussed before, I'm talking about in the language of d star, which is the type, because I'm going to essentially make a connection between the untreated potential outcome and the untreated and the d star. I ask you to wait just a few minutes for me to explain to you why it's useful at all to make a connection between d star and y0. Why don't I go straight to y0 and never even talk about d star? I can explain to you in a few minutes, okay? But the key point here is that I'm going to make this assumption. More specifically, now let me explain what it means here. So that discontinuity here in the selection variable is exactly what allows us to understand that whatever discontinuity I see in the outcome, as you can see, this is the outcome discontinuity after controls were held constant. Whatever discontinuity I see in the outcome here must mean that this delta must be positive. Now I'm just putting a different notation here, but that was exactly the selection effect I was talking before, right? Now I'm calling that delta. It is essentially the key assumption that we're going to make here is that after we control for the selection variable, that is the actual assumption, after we control for the selection variable, in a linear way, you can see that I'm controlling that not non-parametric, but rather in a linear way, the correlation between my treatment variable and whatever is left out in terms of the error is going to be 0. That is essentially a classic selection unobservables assumption, but it's a selection unobservable. We like to call this linearity assumption, because essentially if you were to write this whole error in a way that it would be a non-parametric function of d star, there wouldn't be any assumption because whatever would be left out would be clean. But now, because we're making the assumption of linearity, that is actually whatever comes out could be complex and could be in principle correlated to the treatment variable. We need to make the assumption that it's not. Again, I'm going to show you quite a bit of ways to detect violations of this linearity assumption. But for you to see this, you already get a sense that essentially you have essentially two discontinuities here. Discontinuity here and a discontinuity in the outcome. And actually, I'll be happy later in the presentation if you all make this connection between what we do here and regression discontinuity design. I will be happy to talk more about that, okay? Because there is an actual connection, although less than you might think. Okay, but now the key point, like we discussed before, one of the weakest possible identification strategy is that the moment I made the assumption of continuous treatment effect, plus the assumption that the sign of the delta, again, the delta is this delta on the positive side here, which I don't happen to observe at all. The sign of the delta happens to be the same side of the discontinuity and the outcome, which I do happen to observe. The moment I make that assumption, I can extrapolate to say that this positive discontinuity does imply that this delta will be positive, which because beta plus delta is sort of 0 around here, it would tell us that beta must be negative. That's exactly what we discussed before. I'm just using a more specific kind of notation, okay? Now, and again, it's useful to think about this, and now I'm talking about implementation, and you see how you can easily run this as an OLS regression, okay? The typical thing here that you would do is, again, you write the outcome as a constant plus the average causal function, which in this case I'm writing as linear, but as you will see, you can write this even non-parametrically, although there's going to be some assumption of separability between the treatment, the average causal function, and the selection function, but you can write this non-parametrically too. You decide to identify whatever causal function you decide to describe, but then this part is going to be a decomposition of the full error between a part that we're going to call this linear part, which we get to control for, and whatever is left out, okay? Now, and we're going to make the assumption that whatever is left out is going to be uncorrelated to the treatment variable. Now, if you just take the simple conditional expectation like you do in a regression, what is the average outcome for each value of the treatment variable? You have a constant, the treatment variable function, and then you have this part here. And what essentially what we want here is, of course, we do not observe the selection variable. We do observe the selection variable when the treatment variable is positive because they are the same, but we do not observe the selection variable when the treatment equals 0 because there's some type there that could be very negative or not so negative. We don't know. Now, what we are after here is essentially a proxy for this D star. And here's a simple proxy that turned out to work for us, which is, you can see here, whenever D equals 0, this is turned on, and that is just the average type among people that are 0, that chose 0 hours. And whenever D is positive, whenever you're talking about working mothers that actually work, this whole thing, this whole term is turned off, and D star exactly equals D, right? So that's a simple way to come up with a proxy of D star, because in the positive side, it becomes exactly D, which I get to observe. And whenever D equals 0, I don't get to observe all the distribution of D star, but I will, because I made the linearity assumption, it turns out that knowing just the mean will be enough here, the mean among people who are at 0. Okay? Now, this blue thing here, which is the average type among non-working mothers, I do not know the exact value. This is exactly this value here, this negative value. I do know it's negative. I just don't know if it's -1, -2, minus 10,000. I really don't. And that's going to be key here because we're going to, if you are after point estimation, point identification, you will have to figure out a way to identify this term. I'm going to show you exactly what we can do here. So essentially, the two assumptions that we require here are one, what we call linearity assumption, which essentially means a selection unobserved assumption. After I condition on D star in a linear way, whatever is left out is uncorrelated to the treatment variable. That is the first assumption that we need to make here. And the second assumption is whatever assumption we need to make to identify this blue variable there. Because the moment I identify this blue variable, I essentially come up with a full proxy for D star, and that will handle my endogeneity problem. Now, remember, this goes back to what Marinho was talking about. In our setup, similar to Marinho's setup, you can come up with a whole spectrum of assumptions, a whole menu of assumptions. One assumption that we can do is just we don't make assumption at all to identify this blue thing. You know what we could do? We just guess it. We know it's negative, so let's guess it to be 0.1. Let's get it to be 0.2, 0.3, 1, -10, -1,000, -5 billion. You can always guess that, and after we guess that, we can just run a simple regression of the outcome on a constant, on the treatment variable, and on this new proxy variable that I just happened to observe for that guess I gave. And that's exactly what we do in this plot here. Essentially, in the x-axis, in the horizontal axis here, these are all the potential guesses I do here. And for each guess, I go and estimate the beta hat. So for instance, when the guess is -3,000, I get this beta hat, which is, as you know, as we discussed before, it will be negative. When I guess to be -2,000, I will estimate this beta hat. When when the expectation is -1,000, I get this beta hat and so on. And the key point here is useful for you to have in mind that you will have an asymptote there. So for instance, if you think that this is the true value of the expectation, it will be much worse for you to estimate it to be too low, because if in reality it's here and you estimate it here, it could be actually much more negative than you thought. But over here, if you actually underestimated how, in terms of the magnitude of the expectation, you're not going to make much of a mistake in terms of the actual beta hat. Does that make sense? So that's the key idea here, and we're going to discuss that. But now, for the first time, I'm going to make a connection. I'm going to try to justify why I even talk about D star. Why does it even make sense to talk about D star? Is that now that you do not have this expectation, one approach you could do is to actually try to estimate that based on what happens in the positive side of distribution. Because remember, the moment I made a connection that D star was equals to D in the positive side, now I have information on all the positive side, right? I just don't, again, I do not have information about how this positive side would be, what would be the lower tail here. I know that everybody at D equals 0, there will be types that will be distributed somewhat weakly negatively there. I don't know how weakly. Sometimes it could be something really, maybe all of them will be here for the matter, right? Very negative. Or maybe most of them will be around here. We don't yet know, okay? But one thing we could do is that we can actually try to fit a parametric distribution on the positive side and tell what happens with the negative tail, what is happening with the lower tail. So for instance, that's exactly what those vertical lines over here, they mean. Those vertical lines here, the green one means what if I fit a normal distribution? If I were to fit a normal distribution, the tail is going to look like this, which would lead us to that average. If I instead go for the uniform distribution, the tail will look more like this, which will lead to that blue average. What we have done, and we have done a bunch of Monte Carlo studies, we figure out that the best in practice, the best assumption we could come up with would be something that is still valid in the case of uniform, still valid in the case of normal, but valid in the case of logit and so on, which is just to assume tail symmetry. It's a weaker assumption than normality and uniform because they happen to be symmetric. Tail symmetry just means I'm going to look at just over there. So for instance, if there is 20% here of data here, I'm going to look at the 80th percentile onwards in the sense, and I'm just going to get the mirror image of that, and I'm going to put it there. And that will lead me to this black area, this red vertical line here, which is with the symmetric expectation. And what we tend to, in this example, it turned out not to be the case. It turned out not to be the case because you see the normality actually is more to the left. But we found out in most applications that the symmetric case turned out to be the most conservative ones. It's the most that provides a more negative one there. So if you are trying to go after results like they are negative or positive, you often find that there's going to be room for it to be more negative, but there's going to be very little room for it to be less negative than you have estimated using the symmetric assumption. But what we did in the Monte Carlo studies, and we did a lot of Monte Carlo studies about this, is that we found out that like edge cases turn out to not show up nearly as much in the case of the symmetric assumption as it shows up in the normal and the uniform distribution. And we also did logit and all the others, and the symmetry one, the tail symmetry one, tend to be the most robust, essentially. Now, the other thing I would like to point out here that's kind of obvious, but I think is useful for you all to understand, is that because this part here is going to be estimated, so in the first step, we're going to estimate. So for instance, if we do a normal, we're going to essentially do a Tobit estimation in the first step. And we're going to do a Tobit estimation, then we're going to do the prediction of the Tobit to get the lower tail, and then we get the average. That's usually how you get this estimation of that in that case. And now, the moment I estimate it here, I'm going to plug in my new regression in the second step, and I'm going to run a regression of the outcome on the constant, on the treatment variable, and on the new proxy variable I just calculated based on that generated regressor. And again, because that is a generated regressor, the kind of standard error I'll get there will be wrong, right? Because that is not an actual true value necessarily. That will be an actual estimated, right? So, and that is, so in other words, it will be as if I estimate normal here, yes, I got this point here, but it's possible that I'm a little to the right or a little to the left. So that would mean the vertical amount of uncertainty there will be different because if I'm a little to the right or a little to the left. So that is why you actually need to bootstrap the standard errors. Yes, somebody asked?
So you made a claim there that, in other applications, we've had mostly the symmetric one being the one that has the most negative, in like the biggest magnitude expectation. I would take that's a reflection of the fact that in most applications, we've had PDFs that look a lot like a bell curve. And so if you have something that is a little, more normal, actually, if you have something that is very fat tail, then you're going to have those types of tendencies. But in this application, we happen to have a very uniform distribution, which is the thinnest tail of all of them, which then makes this result not uh, that puzzling in that sense.
Yeah, it makes sense. It makes sense. Yeah. So we have considered other kinds of assumptions that are a little, perhaps using a little more information that some of you might be interested. For instance, another assumption would be right now, you see this blue uh, line there? That comes out of a lower tail that tries to fit a whole uniform distribution on the full positive side. But what if I try to fit only the uniform distribution, sorry, just the uniform distribution, just a little bit above, just a little bit above? You can see that the slope is a little bit more intense there. That means that will be the blue area, will be, the blue triangle will be a little steeper there, right? That will give me expectation that's perhaps a little bit to the right of the uniform distribution. In the paper, we actually do show this as a potential interesting lower bound about if you are willing to assume that the uniform is as steep as it gets and it cannot be further from here, then you know that the effect can be not be too negative. Regardless, the effect, as you know, based on the results we showed before, happens to be negative already, okay? Yes. Deborah?
I have a question that it's more to the application when you have very high level of bunching, because if you are talking here, you're talking about a level of bunch of 20%, I think. If you have bunching levels that are above 50, for example, you cannot use just a tail.
So I can promise you, I did not ask Deborah. Deborah is my co-author. I can promise you, I did not ask Deborah to ask this question. But essentially, Otávio is going to present a paper tomorrow that is going to deal with this problem, and is going to deal with that non-parametrically, not parametrically, okay? Which is going to be useful here. Okay. Now, that's why we need to bootstrap the standard errors, okay? So we need to bootstrap the standard errors exactly because this part that comes in the second stage as an estimator. And of course, we have code of all those things in my GitHub, and Deborah as well as Hugo are actually trying to work on a new package, and hopefully it's going to be ready soon. Okay, so now let's just talk about the whole spectrum of potential assumptions that we had in mind. The first one was the weakest possible one that in that setup that we came up here. That's just assuming continuity of the treatment effect and the same direction as zero versus at discontinuity at zero versus the sign of the selection effect on the positive side. That comes out of doing plots like that, like we talked about, right? The second one will be to actually not only look in here, I'm going to try to assume that the selection marginal effect in as zero and the selection marginal effect in the positive side will be the same sign. I can actually make a stronger assumption that not only they have the same sign, but they have the same quantity. That's exactly what linearity assumption is. The marginal effect is constant. The marginal selection effect is constant. That's exactly what we're doing in this setup here. And in that case, you just need to run a regression of the outcome on a constant, the treatment variable, and the new control variable that proxies for the selection variable, which is this one here. And for that, you need two assumptions. First, that controlling for the selection variable in a linear way is going to be enough to handle the homogeneity problem. And second, whatever assumption you need to make to get to the average type among people that are equal to zero, okay? So now, in principle, you don't need to make that assumption at all. That's what I do in this overplot here. I just don't need to assumption, but then I can only create bounds. I can only show the range of potential beta hats you can get for every possible potential value of the expectation. But I can actually cross that with potential vertical lines, which is specific estimates of the expectation coming from usually from the positive side where I observe the distribution of these stars, okay? And of course, it's useful perhaps for you all to understand that, for instance, exactly like what Carol was suggesting, you do observe that it's fairly similar to a uniform distribution here. You do observe, for instance, that the CDF here in the positive side looks very different from a normal distribution CDF. So that's the idea that in principle, if you make a distribution assumption to get to the expectation, of course, you can use the positive side to test it, right? You can actually do the classic Kolmogorov tests where you can actually look at the actual empirical CDF and compare that with the predicted CDF based on the normality assumption, and you might see that this would already be, that violation would already be detected. Of course, it's much harder to detect the tail symmetry here. It's easier to detect the symmetry because you just look at the distribution over here versus the distribution over here when you still get to observe. But tail symmetry, by definition, I'm just looking at the tail, so I cannot detect that. You will see in papers that are going to be presented later that actually this is detectable. This is detectable, and that for a long time we started thinking, but wait, we can detect violations of linearity, we can detect violations of these parametric assumptions we make. So where is the limit here? What can you not do? And then Carol is going to present a paper tomorrow that gave us this anchor to understand what is going on. Is that unlike the setup where Marin was presented, where you have problems of non-parametric non-identification, this impossibility that Marin was talking about, we actually have non-parametric identification in this setup. So all these assumptions we are making here, they are not necessarily they're not necessary for you to actually get identification. So you actually could, in principle, test them all. Okay. Again, I would like to remind you that this is not necessarily true. There are assumptions that Carol is going to present, that is going to make there. But one key assumption that is going to show up there, somewhat related but not identical, is this assumption that I told you about this type, the direction of the effect that I find as zero and the direction of effect that I find in the positive side, at least just in the positive side, is going to be in the same direction. But I would like to remind you again that there is, in the whole manual of assumptions that we make here, there is one approach, which David is going to present later today, that does not make this assumption, okay? It makes a different assumption. Okay, so now I told you this is kind of like the two extremes in this scenario, right? The lowest, the weakest possible kind of assumption you make versus the strongest possible assumption, which would involve the linearity assumption plus the tail symmetry assumption, okay? But now I would like to tell you that there are two ways to dial up and down the kind of how strong the assumption turned out to be. And that relates to the idea of which kind of estimate parameter you're after, and also which kind of controls and which type of controls you get to add. So let me explain to you this intuition, because that goes exactly into the idea of how to implement this in a way that you can convince yourself that you are okay, versus you can convince yourself, no, there's something here that I cannot do, okay? So the first one is, like right now, I'm just showing the discontinuity plot of the outcome, and you already can see that there's something weird happening around here, right? Like from 2000 hours and above, you do see some kind of evidence of nonlinearity there, right? But again, then this is, as you know, this lope here, they not only mean selection, they mean treatment effect and selection effect. So, but you already see that perhaps there's the linearity assumption is not that bad of the treatment effect plus selection effect up until around 2000 hours, but then something weird is happening there. Let's say that, forget about controls for now, let's say that you are okay with a linearity assumption that is much more local. This goes back to what the classic idea that is that you might argue that global linearity might be much stronger than local linearity, right? So you might think, okay, so I am not okay with assuming the selection as zero is the same as selection at 2000, the marginal effect of selection there, but I'm okay arguing that the selection as zero is the same as the selection just for the first 50 hours. If you are okay with that, then you can go back and say, okay, so from now on, I'm after the average treatment effect only for the first 50 hours. If you are just focusing the estimate only for those first 50 hours, then you get to identify something under a more local linear assumption. Does that make sense? Similarly, if you are okay with this very strong assumption that is linear over this selection, the reason you have this nonlinearity here is not due to selection effect, but rather due to treatment effect, then you are okay saying that yes, the treatment effect is going to be higher, more intense here. Okay? You had a question?
Yes, I do have a question from Miles Kimball.
Yeah.
Here online, and he's saying, how about the following? So I think this refers to the previous slide.
Yeah.
So how about the following assumption? The observables account for all of the endogeneity, except that each of the observables is measured with classical measurement error, with an unknown variance of the measurement errors.
Yeah.
So it seems that something could be learned about the sizes of measurement error variances given the magnitude of the jump at zero.
The observables are measured with measurement error?
Yes. So the observables are measured with classical measurement error.
Yeah. So the first thing that would, let's say that I am in a situation like that, and let's say a referee or a person is asking me questions like that. The first thing I would point to a person like that is to say that if indeed those observables will be measured like that, it will be actually hard to observe this kind of discontinuities I observe in the in the observable variable. The discontinuities I observe in the observable variable here, it'll be hard to observe that, particularly because the key idea here is that it's possible that observables tell us nothing about what is happening to unobservables. But the fact is, if observables are varying, are somehow ineffective whatsoever to control for potential unobserved heterogeneity, I wouldn't be seeing something along the lines of what I'm seeing here, which is a reduction of both, sorry here, a reduction of both the slope as I control for things from here to here versus the reduction of the discontinuity here. In fact, this tells me that there's something interesting here. The slope speaks to the selection in the positive side, right? The slope, the changing slope, it speaks to us about how controlling for covariates reduce the selection in which direction on the positive side. And the reduction in the discontinuity speaks to us how adding covariates reduce the amount of selection at zero. And you can see that they both go in the same direction. You see that this is actually reducing and this slope is reducing. That is actually key for you to think about issues of whether the covariates are in any way meaningful ways to handle the endogeneity.
I'm going to, so Miles says, I'm thinking that the size of the jump at zero would vary depending on the assumption about measurement error variances. There are some measurement error variances where there is no jump. It is my impression that his point actually is probably true, is that you could actually do something.
I do think that it relates somewhat to the paper that you're going to present tomorrow and relates to the convolution. Anyway,
I think actually that's in some sense that's a good scenario for bunching type techniques because usually what we need when we so we have this assumption, most of these methods have some assumption where you have like a continuous treatment effect at zero, and then you need some assumption that there's something representative about what's happening at zero versus elsewhere. And so to the extent that this measurement error is something that's happening both at zero and elsewhere, if it's happening in both places to the same extent, then the sorts of biases that we're picking up by looking at with our sort of microscope at selection bias at zero is going to be representative of what goes elsewhere. So the sort of extrapolation that we're doing here in this paper is something with, assuming linearity about how D star enters in the Y equation, and the paper that I'm going to present later today also has an assumption about how you extrapolate away. I think actually, in some sense, the application that I'm going to talk about this afternoon is pretty much precisely this, where there is a confounder which we measure with noise with various observables. And so hopefully, I mean, I won't give my talk now, but will be related to that.
Exactly. That will show up for sure much more intensely in that paper. That's true. Okay, so first of all, I would like to shout out Miles, a friend of ours who is from Colorado Boulder. I'm happy he's there. Okay, now let's go back to the key idea then. So, like I said, one possible way that you can actually dial down if you think the assumption of linearity is too strong is to go more local and focus yourself on an estimate that is more local. But just to be clear, you can see that this linearity, and again, I repeat, this is not necessarily linearity evidence of the selection, right? Because this is treatment plus selection. But you can see that the linearity assumption essentially goes, the non-linearity kind of goes away the moment you add controls here. This is much more, this is exactly the same y-axis, just to be clear. And you see that this is fairly linear after controls are added. So that, again, you might be, this is another way that you can actually dial up or dial down the assumptions by actually adding controls. The moment you add controls, it actually may weaken the assumption, because again, the idea here is that when you add controls, and we're going to discuss later, you now are saying that after you add controls and after you add the D star, which is the selection variable, whatever is left out is going to be assumed to be uncorrelated to the treatment variable. Now, I would like to now talk a little bit about implementation with controls, because I honestly think that that's where this method can actually be particularly helpful, because you'll see that it's going to be particularly scalable to go after heterogeneous effects. Okay, so the only thing that I did here was I just added a bunch of x's in parentheses here, okay? So instead of having a model of the potential of the untreated potential outcome like that, which assume linearity, I'm now assuming linearity condition on x, right? This alpha here, you can think about for now x as a discrete variable. It takes all like 100 values or 1,000 values or something like that. For every value of x, I'm having a dedicated alpha and a dedicated delta there. So I'm essentially allowing for it to be nonlinear only to the extent that it leads to changes across values of x. But within a given value of x, it needs to be assumed linear there. So that is the key assumption here. And you can see that you can totally relax the linearity assumption a lot, but now you enter in this regression. Again, these are regression coefficients, so it's easy to estimate this whole thing, but you essentially have the linear coefficient, which now varies with x, the average causal function, which now you might allow for a heterogeneous effect based on covariates, that you can do that for boys versus girls, for rich people versus poor people, and so on, right? You can actually specify beta according to several values of x you want to specify. You allow for the selection variable to vary with each value of x, but you also allow for the average type among people that are among mothers that are not working to vary depending on whether you're talking about boys versus girls, rich people versus poor people. Remember, this was exactly something that we did find. When we look at the CDF for low skill versus high skill mothers, those CDFs look very differently, right? So it's possible that the value, the lower tail of them will look very different indeed. So now this is exactly, you essentially can mix and match. You can choose however you specify either of those four ways that in which x is entering here. It's entering here. Of course, you can add x linearly the way I did before, x times gamma, like before, but you can also add in different ways. I'm going to explain to you in a few slides exactly how else you can do that to go, say, to approximate a non-parametric function of that. You can estimate, oftentimes for you to keep your paper with a more clean narrative, you might want to restrict yourself to a few dimensions of heterogeneity for you to focus on, but that's what we have done in many of our papers thus far. You can actually talk about the selection effect, which you will see. You can also allow for that to go non-parametric, this delta of x, and you can allow this expectation to be well approximated by a non-parametric as well for different values of x. So now, again, this is just a simple regression, right? You just regress. At the end of the day, you're going to regress the outcome on not necessarily a constant here, but rather a bunch of coefficients of covariates. It will be a constant too, but it will be a lot of coefficients of covariates. This will become just alpha plus x gamma if you just add x in a linear way. You're going to specify beta in whatever shape form you want. In principle, you could specify beta as just beta like I did before. You can specify selection variable as essentially you can interact with a bunch of controls and so on. And you can actually do this estimation here. But now the estimation is going to be dedicated for different values of x, like here. And again, the two assumptions now will be, yes, somebody asked a question, I think? No, okay. The two assumptions will be now you have after you condition on controls, the treatment variable and whatever becomes the remaining error there, which is the error of the equation after I add controls, it's not here. Of course, it's related to that eta there, but that eta only speaks to the untreated path. It also, you have to understand that in a world of heterogeneous treatment effect, there could be other kinds of errors there too. But essentially, whatever is the D versus epsilon will be uncorrelated after I deal with controls. And the second assumption will be that you can identify the average type among the non-working models of a given type defined by the controls, okay? Now, the idea here is that you are weakening those two assumptions that we made before. The first was you are allowing for nonlinearity of the untreated potential outcome to the extent that that nonlinearity changes across values of x, right? And the other thing is that you are allowing for asymmetry of the distribution of D star, of the selection variable, to the extent that that asymmetry is picked up by different values of covariance. I'm going to be much more precise in the next slide or two about this, because it turns out that that's going to be very useful for you not to relax, because this is something about controls that people don't think much about, but I think is very useful. Similar to medicine, right? Oftentimes it's much easier to figure out that there's a problem than to find the solution of the problem, right? So it turns out that controls are particularly, sure, they relax the assumptions, but they're particularly helpful if you use in a certain way to detect that there's an issue. And sometimes you're going to be able to detect the issue and you're going to figure out, okay, I'm done. This is bad. I cannot do anything about it. But you see that detecting the issue is going to be much faster. It's much easier than to actually solve the problem. And controls are very helpful for that. I'm going to explain about how you do exactly what I just said. How do you get, and I think this is, of course, you don't need to run this implementation if you think that the linearity assumption is fine, if you think the asymmetry assumption is fine, or if you don't even want to make those assumptions whatsoever, you just want to make the weakest possible assumptions just to get at that bounds that we talk about, the weakest possible. But now I'm going to tell you why, if you are to make the strongest assumptions, namely the linearity assumption as well as the tail symmetry assumption, how you get to detect whether there's a violation of them, okay? And how you get to figure out a test that gets to be powerful to detect that if it happens to be invalid, okay? So the key idea here would involve this idea of discretizing the covariance. By discretizing the covariance, I mean I'm going to just allocate different observations to different groups, or we call clusters, depending on how similar these observations are related to covariance. So for instance, if you have like 50 different covariates, of course, if you had just one covariate, you just look at, and the covariate will be age, I would just group people based on age, right? If I had just gender, I will group people based on gender. But what happens if it's gender and age? I will group based on gender and age together. But very soon, these cells become very small, right? So cluster is essentially a way that you can scale up this pretty well to talk about all different dimensions of the covariates in a way that you can actually modulate. Okay, so I would like 50 groups, I would like 20 groups, I would like 100 groups, and so on. So the idea here is that the more clusters you add, the more likely is for the observations in that cluster to be more similar to each other. And the less groups you have, they're more likely, as if you were not, if you put everybody in one bucket, you're not doing anything, right? Everybody is essentially the same, in the same group. But if you put in 100 groups, now everybody is allocated to one and only one of those 100 groups. That's going to be helpful here because what I'm considering here is to specify all those functions before, all those blue functions that relate to the endogeneity problem, namely the alpha, the delta, and the expectation, all those three, I'm going to specify them as like a fully saturated indicator variables for for whether that particular observation is in a given cluster. So if I have 50 cluster, I will have essentially 50 controls here, and I'll have 50 controls here, and I will have 50 different estimates of this, okay? So that's the key idea. Of course, I don't need necessarily to specify the average causal function that way, you will see actually, you might be worried about, well, Greg, if we do all these kinds of major specification that is not parsimonious at all, your standard errors are gonna suck, right? You're gonna be terrible. But remember, if you go after beta hat here, if you don't specify the average causal function the same way, if you only specify beta instead of beta per different cluster, you are essentially going to integrate across all those observations at the end. So you look very much like, as you all know, when you add a bunch of fixed effect in a diff in diff in a two-way fixed effect, it's not like the standard error of the estimator is going to go up a lot because there's a nuisance parameter, right? It's the same idea, okay? So it turns out that you can do something like that. And here's what happens when I do that. And that's going to be useful. Before I show this, I'm going to show this is the plot. This plot happens when I have one cluster, which is nothing. I essentially have one cluster, and one indicator means essentially the constant, right? Versus all the way to 100 clusters. And essentially the beta hat barely changes when I do that. Now, you might ask, what does that tell us at all? Does that tell us something? And I'm going to actually convince you here that actually sometimes it doesn't tell you. I will show you why it may not tell you. But in this application and in some of the applications that we have done, it provides some useful information. Let me explain to you why. Here, I just fix a given number of clusters. And now we have 50 clusters. Now you essentially have a total of 50 clusters, and I sorted them all based on the lowest median of the treatment variable all the way to the highest median. So for instance, the 50th cluster that I call 50th cluster here, the median is 1,500 hours. So across all observations in that particular group that I call cluster 50, the median people there, the median modelers work exactly 1,500 hours, okay? And by the way, those vertical lines here, this is the interquartile range, this is the 25th, this 75th percentile, and that is the 25th percentile, okay? Now, I do the same all the way to all clusters, and you can see here that the median is 0 for the first two. You see that the median for the first two clusters is 0. By the way, just so you know, there is bunching across all 50 clusters here, okay? And that goes back to the idea that bunching is a fairly prevalent variation that allows you to do a lot of testing like that. So the median bunching, the median variable value here is 0 for those things, and the interquartile range here will be the 75th percentile will be, I guess, 300 or something like that, 300 hours, and the 25th percentile, of course, is 0 in that case. But the key point that I want to argue here is that I hope by now you start seeing that the overall distribution of D star changes a lot per cluster. This is the distribution of D star from the 25th percentile to the 75th percentile, because it happens to be all positive. I do observe that part of the distribution because that's D, right? That's the selection. The selection variable in the positive side is equals to the treatment variable. So the distribution here is very different than the distribution here in cluster 25. That is helpful because, and this is the key idea, as I'm controlling for X, I'm indirectly allowing for that kind of nonlinearity that I was worried about, right? I am indirectly allowing for nonlinearity because as I'm doing a fully saturated regression by different cluster, I'm picking up at least partially the extent to which the selection variable may change from one value of the selection variable versus another value of the selection variable. And this happens even at 0. As you can see, the distribution is, I just happen to observe the treatment variable, the selection variable only on the positive side. But this is suggested that the selection variable is also changing on the negative side in ways that I cannot observe. I'm going to show you much more clear evidence of that in a few minutes. But the key point here is that the fact that this, as I'm relaxing all this non-linearity assumption, if it happens to be nonlinear, and yet I am allowing for this, for more, as I'm adding more clusters, I'm capable of picking up at least partially that nonlinearity, and yet the beta hat, after I integrate it all, is not really changing. That is a valuable information. That is not only about nonlinearity, it turns out. The reason why I like this particular plot, and that's why we show this interquartile range, is that even the asymmetry assumption is actually, the symmetric assumption is being tested to, right? Because right now, as you can see, the midway point is kind of here. So, and the median is above for that cluster, the midway point. So clearly there is asymmetry here in that distribution, right? Clearly there is a different kind of asymmetry for this other cluster. It turns out the halfway point is a little bit higher than the median point for cluster 25. So, and of course, it's crazy here, right? So in other words, I am allowing, as I'm picking up different dummies, different indicators per cluster, I'm picking up also the likelihood that some of this asymmetry can be picked up by those covariates I'm adding. And yet, when I do all of that, this is what I find, okay? So that is useful. And again, I will be happy. Josh, you had a question? It will be very uninformative because of the issues we talked about. So my understanding, Josh, of your question would be, what happens if you were to report the beta hats of X? And you'll be very uninformative because of the issue of integration, right? You really, then you are estimating for each of those cells a dedicated beta hat. So the advantage of that is that if you integrate, if you aggregate them all back, of course, you aggregate them all based on. Yeah. Yeah, I see what you mean. This is a very useful thing. You're right. This is a good thing we have not done in this paper, but particularly in this paper is a useful next step to do, right? Because the moment I find that even when I go from 1 to 5 or 1 to 10, nothing changes, and this is going to continue like that, maybe I show you heterogeneous results per cluster over there. And I could, in principle, even project all those clusters onto actually observables to have a more understanding of the condition of ATT. Okay? So this is just to end. I'm going to just show you the FAQ here. I'm happy to ask any question, but the key idea here is that what if the D is actually not a continuous? It turns out that if you use the same kind of RDD, you should be fine. Can we control for observables that only show up in the positive side? Yes. You're going to have to see the paper that Eric is going to present after lunch. Can we obtain an estimator of that, of the expectation, without having to do this kind of projection out of sample to talk about lower tail? Yes, please see the last presentation of today when David is going to present this. And do we need to make parametric or linearity assumptions? And the answer is no. It's actually in the paper that Carol is going to present tomorrow is going to show that is non-parametric identified. And the paper that Otávio is going to present tomorrow is also going to show that is non-parametric identified. And can we test for nonlinearities happening solely on the negative side? It turns out that what I just showed you is testing that. Is testing nonlinearities. I'll be happy to show you more about that if you have any questions.